No.
What is this?
Two things I want to say. First of all, there's a little bit more geometry than I expected it has. So, for many students like here, I see who never saw anything like that. And Dil asked me to do this because he himself didn't have geometry, so he couldn't do it. So that's why we probably this one and maybe the next one. And second, the notation is certainly, even if you had it, it's very kind of different. Okay, let me put it that way. Well, I didn't like part of it, so fine. Well, notation is like your habits, like, I don't know, your friends. I mean, you get used to a certain style, and then you use it for the rest of your life, even if it's not the best thing, but that's what you can do, that's what you understand, and you shouldn't change it, and it's just fine. Okay, so, well, let me just go over this, and I'll try to present kind of the minimum what is necessary for the, because otherwise this will turn into just geometry seminar. It's just too much. Like it starts with the geodesics, then metric, then covariant derivative, connection, then differential forms, a lot of differential forms. And he needs that to discuss later on the Hamiltonian system and the symplectic structure. Well, but he doesn't need all of it, okay? So maybe he needs it some later in the book. But that's why I'm not going to do everything that is in those sections, okay? So, well, if you already have geometry, then you'll be fine anyway. So, and I'm going to do it in a different order because, well, when you do geodesics, you're basically minimizing a functional, and then he does this first in two different ways, and then he goes to the next section and talks about variational problems in general. Well, we feel that it's much better to do it in general first and then specialize it into that, and then you'll see what happens. Okay, so let's just start this way. So these are variational problems. Probably in one dimension so that we will get an ODE. So, well, you could do it in manifold, but since you don't need to know what a manifold is, let's assume that you have Euclidean space, Rn, and you have this is an open set. So this will be just an open set in Rn, which is fine. And then we have some functions of those, well, let's say, well, in physics they call them Q, they call them generalized coordinates and so on, but well, let me use that notation. So you have Q, which is a vector, Q1, Qn, okay, and so I'm going to write it just like Q9. So I'm going to call this coordinates. So these are coordinates. And not necessarily Cartesian coordinates, but just some coordinates. So there are n variables. And then we look at just an open interval. So this would be an open interval. No, not open, closed. It doesn't matter at this point. And then we look at these maps like this. Well, let's say I to M. Okay, and so these would be, well, let me call it Q. Well, let me call it gamma. So, well, this is a map. So what does it do? It takes T, and then it maps it to gamma of T, which lies, it's a vector in I. Okay, so basically what this is Q, well, you don't need to write, well, if you write this, then you can do this. So, and that gives you a curve. So this is a curve in F. Right? So, and then we look at the family of all curves. Just suppose there are all possible curves. And so now, well, let me sketch this is M, and I'm going to fix the endpoints. So, well, let's call them somehow. Let's say Q0, well, let's say Q1 and Q2. Oh, okay, A and B. Oh, fine. No, 1 and 2 is not good. Well, yeah, P has P and Q, well, but I already used P and Q. Yeah, that's fine. So these points are fixed. So in other words, these are the endpoints of these curves. So in other words, Q of A, no, Q of A is Q1, and well, let me call this P. Well, that's fine. It doesn't do that. And this is Q2. So these are endpoints. So, and I look at the curve. So this is a curve with fixed endpoints. So these are fixed. So I introduce this space of all, well, this is at least continuously differentiable, or let's say twice differentiable, but you could just say smooth curves, okay, smooth. So all these functions are smooth, all derivatives exist, and they're fine. And so you look at this space, well, you could call it any way you want, but well, let's just call it P for paths. These are paths from one point to another. And so the, well, these maps that are, well, let me call it gamma. And so they see infinity, which means that these are smooth and such that, oh, you know, let me write. So this is interval M, and so such that they are smooth and the endpoints are fixed. So that's my space. All possible smooth curves that connect to points. And I limit myself to the situation when these points are close to each other. So, well, this is local description, so consider these points to be close and not far apart, because then, well, then there are some issues that I don't want to talk about. But let's just say they are close enough, and then well, you define a function now. Let's say first you pick a function. Oh no, before that, so you have coordinates, like this Q of T, and you have velocities. And let me call velocities Q dot. So this is v by dt of Q. So there are two n variables. There are n of these and n of those, right? So there are two n variables. Q1, Qn, and there are Q dot 1, Q dot n. Two n altogether. Okay, and so now I consider, well, let's say a smooth function, which is a nice function that I'm going to call Lagrangian. It's such a pleasure to write on this board, you know, I already forgot that feeling. Blackboard, it's like going back, meeting old friends, and, you know. I would stay here. If you can leave, I would stay here.